Hello, everyone. Welcome to the third Friday of our February flare-up focused on climate. We're really glad that you were able to join us. And we wanted to take just a couple minutes at the very beginning to recognize, particularly the University of Alberta, since that's where our organization is based. We wanted to acknowledge that the university and many of their facilities are located on Treaty 6 territory. And we make every effort to respect the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. I also want to note that we have representatives on this call from across Canada and beyond who live in areas both under treaty and also on unceded lands. And then just to take a couple minutes this morning, I wanted to just raise a couple points about the UN Declaration on Rights of Indigenous Peoples, or the UNDRIP. As most of you are aware, Canada has committed to the actions in that document and in that declaration. And that includes basically commitment to take steps to address injustices, combat prejudice, and eliminate all forms of violence and racism and discrimination, including systemic racism and discrimination. It's also to promote mutual respect and understanding, as well as good relations, including through human rights education, as well as to implement measures related to monitoring, oversight, recourse, or remedy, or other accountability measures with respect to the implementation of the declaration. When the legislation was filed, the national chief of the AFN at that time was Prairie, and he made this comment. He said, "This legislation to implement the UN Declaration on the Right of Indigenous Peoples in Canada can be a pathway to reconciliation guided by our inherent and treaty rights. Its full implementation will see First Nations respected and implemented and is essential to addressing all forms of racism and discrimination in Canada. Many of us who are settlers will deal with Indigenous communities in an official capacity, and all of us will work with Indigenous people in some form or another. The UNDRIP framework can serve as a reminder of both historical wrongs and the future that we can aspire to." So this week in February flare-up, we're looking at the aspects of climate and climate change, spending a little bit of time looking at available data sets, some examples of scenario selection, some best practices, appropriate use and limitations. We'll also hear about ClimateAtlas, ClimateNA, and FWI Climate Change Projections. So we're pleased to have a team of presenters that include Ian Mauro, who's the Executive Director of the Pacific Institute for Climate Solutions, Christey Allen is a research manager, and Matt Loxley, a research associate with the Prairie Climate Center. Andreas Hamann, who's a professor and associate department chair of research and communications at the University of Alberta. We also have Tongli Wang, who's an associate professor, Department of Forest and Conservation Sciences, University of British Columbia. And Jeremy Fyke, who's a coordinator of the Canadian Centre for Climate Services as part of Environment and Climate Change Canada. We'll have a few minutes between topics or between groups or discussions for questions, just in case there's something really burning and urgent. And then we'll also set aside time at the end if other questions come up. Probably the easiest is to type your question into the chat, and we'll sort of assemble those, and we'll also try and group like questions. And you can sort of type those in at your convenience. And so without further ado, I will turn over the floor to our presenters, and we'll let them take over. Thank you very much and welcome. We're really looking forward to this.
Hi, everyone. So I'm Ian Mauro, the Executive Director of the Pacific Institute for Climate Solutions. And as was mentioned, Christey and Matthew from the Prairie Climate Center are part of the presentation team. And we wanted to speak on wildfire climate and storytelling and focus on data diversity for decision-making in terms of, we're talking about climate data, but also other types of input into these climate conversations. And Christey, Matt, any kind of opening remarks from the Prairie Climate Center perspective?
Yeah, I think it's just touching really on how you can integrate different types of data information to really effectively make decisions in adaptation planning and kind of planning for the future in a resilient way. So with no further ado, we can talk about that in depth.
Yeah, so we'll jump into it here. And as you'll see, the kind of PICS Prairie Climate Center connection is emerging. I was the former executive director at PCC, and so we're still collaborating in some interesting ways. And before we get started, we want to acknowledge the traditional territories that we're coming from. We're all of us right now, Christey, Matthew, and myself, on Lekwungen speaking territories here in Victoria, the areas of the Songhees, Esquimalt, and Wasanich people. And I also wanted to kind of point out this, if anybody who's in Vancouver, this exciting presentation at Science World, talking about the canoe journeys on this coast. And I've actually had the great privilege working with Hereditary Chief Frank Brown, his daughter, Copper Canoe Woman Vina Brown, on talking about the Indigenous cultural resurgence of these canoe journeys. And when we speak about land acknowledgements, this is one of the areas where I really learned what a land acknowledgement is. And Tribal Canoe Journeys brings people together by canoe to bring back the canoe to the waters of the West Coast and the whole Pacific Rim. In a certain sense, it's quite an international project. And when the canoes gather and they go to a territory and they raise their paddles, they ask permission of the host community if they can come ashore in a good way, and they acknowledge the territories where people are joining, and to see that in practice, and to see that real acknowledgement of people interacting with each other's territories in a really, really thoughtful and respectful way, was a real eye-opener for me as a settler and as a scientist. And so that's something that I carry with me here and try to practice, in my work here in BC. And so just something to share with you around our journey, but also some of the activities here on the West Coast around cultural resurgence and whatnot. So on that theme, and the opening that Brian provided around, the importance of reconciliation as we talk about data and we talk about these issues, we want to bring your attention to a video that we made with BC's AFN Regional Chief Terry Teegee. And I shot this film with a team a number of years ago up in Prince George, and it really does help us set a context for climate change and for thinking differently about how we approach these issues. And so this is a bit of a longer piece, it's 4 minutes, but we want to set the context in a good way, and we thought this film would be a nice way to start. So actually just want to make sure, I don't think I hit the audio on my screen sharing, so I just have to get this going. Here we go. And let's get the video going.
When you realize where your food and your nutrition and your medicines are coming from, you have a greater appreciation of what this area is, of what your land is. We've lost that real connection with the land. And I think we're seeing the result of that, and development and Western ideology and politics and capitalism all plays an integral part to how we develop land, how we use land, and there's an imbalance, and that's why we're seeing not only in British Columbia but around the world climate change, and in the end we all have to pay the price. A lot of the issues with climate change stems back to how humans are involved in the forest. We're seeing a lot more forest fires because there's a lot of mismanagement. And one of the biggest issues is that we don't allow forest fires to take place. So we have an area of forests that are old and decadent, and that's a big problem. What we've learned through generations and generations and hundreds of years is that the fire is a very integral part of the forest. There's a certain window in time where our people, through our villages or in our land, would go out there and create fire. Over the last 100 years, we've taken that very integral part of the forest that, restarts the whole initiation of renewal, regrowth. If there was a lot more renewal, different species of trees would come back. A lot of our Indigenous people rely on what's coming out of our rivers, the salmon, the fish, and what's coming off our land, whether it's the beaver, the muskrat, the moose, the bear. We have a greater appreciation of what is basically a gift from Mother Nature, from the Creator. And in that way, we have a great appreciation of the land and what it can provide for us. And even within our culture, we give tobacco, we give smoke, we give thanks to the waters, to the land. And it's that connection that's missing in Western society. I think as an Indigenous person in Canada or anywhere in the world, I think we could be a catalyst for change and realizing that, you know, some of these things are worth fighting for, and basically we have to hold up each other, we have to support each other, and we have to make change. And, you know, it's not only Indigenous people, but it's people around the world that need to make change. One person, you know, it's 100 persons, it's 1,000, it's 1 billion that have to change their behavior. Until we overcome that really dominant paternalistic ideology, that, you know, we'll realize, you know, we have to do something now, and we have to control our behavior as human beings, and we have to do something about climate change.
So that film was shot as part of a larger film that I made called Beyond Climate, which is about climate change in BC. And this was before the big forest fires. This was shot in 2014 to 2017. And that's a film that you can watch online. Regional Chief TG is a registered professional forester, but also is speaking, you know, from his perspective as an Indigenous person, as a First Nations leader, and that Indigenous wisdom and knowledge. And so when we talk about data diversity, we're talking about climate data, but we're also talking about different forms of information that can help us see the world in new ways and new opportunities for change. And since coming to British Columbia, the heat dome, you know, the extensive fires, the atmospheric rivers, we know that we have lots of work to do. And that idea of seeing things in a new way is really, really important, because even with the best available science, we're still not entirely certain how to deal with these huge challenges. And so thinking broadly, thinking about diversity is really, really important to the work that we have done collaboratively at the Prairie Climate Center, and now with my work at PICS. And with respect to PICS, Carly Phillips here, one of our researchers in residence, leads the Wildfire and Carbon Project with Werner Kurtz at the Canadian Forest Service, and they're looking at, you know, the carbon kind of capture and capacity of the forest to retain carbon, but also the impacts of wildfire and what that means for, you know, carbon management and also the bioeconomy. And so there's some really exciting work happening at PICS here that we're involved in. But to kind of step back, you know, the World Economic Forum just released this global risk report. You know, when you take a look at the next 2 years, cost of living and all of these things, geoeconomic confrontation, but over the next 10 years, it's all about climate change, extremes, natural resource crises in terms of, you know, global risks moving forward. And we can really see those environmental risks being something that we need to be getting a grappling on. And so, again, I appreciate everybody being here this morning to talk about this and to talk about these interconnections. And so this is another figure from the Global Risk Report, you know, the green, how climate change is connected to all of these other issues. And so, you know, these stories are really, really important, how things connect. And this is an example of us pulling in different kind of forms of data and how we use cameras to kind of interact with communities and build stories around awareness that lead to kind of despair when we think about these things, but how you come out of that looking at hope and action. And so that's things that drive some of the work that we've done collaboratively with the presentation team here today. And in that kind of trajectory, we actually decided to build the ClimateAtlas of Canada. And the ClimateAtlas of Canada is the first national climate portal. It was launched with then Minister of Environment, Catherine McKenna, in 2018. And it brings together the data and these stories that we're talking about, this kind of different way of knowing people on the land, Indigenous people and local knowledge holders, to think through and, you know, these connections and opportunities for applied adaptation. And on that note, I'm going to pass it over to Christey.
Yeah, so today the focus, we are going to do a bit of a deep dive into the ClimateAtlas and looking at the data, but I'll give a bit of a high level overview of how we've brought things together to integrate those diverse data types, because what we really believe in at the Prairie Climate Center and Ian at PICS as well is that you need sort of this transdisciplinary kind of diverse approach to really understand data and really apply it. It's not something where you can just take a number and understand what that means in the real world. So it's really how do you interpret it? How does it make its way into a decision-making process or a planning process? And so we really like to bring together all of those elements, because that's what you need for fulsome understanding of what a future climate will look like. And so here we have on the screen the ClimateAtlas of Canada, and we kind of collaborate with PICS and PCIC and the folks at Climate Data to kind of bring together the best available climate data. We have Dr. Danny Blair is our main climatologist on staff, and you'll have Matt coming and talking to you in a little bit. And we really have like a strong back end with the climate data, but bring together our filmmakers and our adaptation specialists to make it a fulsome product. Next slide, please. So in addition to just having data, we provide elements of how to interpret data and how do you bring that into the real world and how do you make it accessible for people. And so we often take these concepts of the data, some of the numbers, and move them into reports and start to really flesh it out for people as to what that means in the future. And so here on the screen, we have this heat waves and health report that we did a couple of years back, and it really takes these numbers of what does an increase in plus 30 days look like? And it's actually, it means things for people's health. And we do that through data visualization and plain language writing and starting to break it down across the country, because a heat wave is different in every area of the country. If you get 1 plus 30 day in Yellowknife, that's ridiculous. If you get 1 plus 30 day in Winnipeg, that's nothing. So it means different things in local contexts as well. So next slide. In addition to interpretation, one of the other elements that we really focus on is these diverse knowledges, but also how to get people using those and understanding them as well. So we've done some trainings that are focusing on how to make practitioners, individuals just really understand that it's not just climate data that we're using, but also these diverse knowledges, Indigenous knowledges, community knowledges, local knowledges, and being able to understand how to apply those is a really important element as well when it comes to considering climate data and information and planning. So it's how do you get people in a space where they even understand the information enough to effectively make decisions? So we've done a fair bit of work with the training side of things as well. Excited. And the other thing that's having the information in the ClimateAtlas and the climate data information as well is it leads to this fulsome adaptation planning process. But the one thing that we've really learned is it's the climate data that comes out of the atlas is just the first step of it. And then there's this really long and really fulsome process that you have to do collectively to integrate the knowledge of community members, people who are working on the ground and seeing kind of the impacts in their own space to pull together what is adaptation planning. It's not something where you can just hand off some climate information and say, here you go, you've got a plan. It's really this kind of connected process of conversation and facilitation that helps move things forward as well. And so that's one of the elements that we really try to pull on. And it looks really different in lots of different contexts, and there's lots of different data that comes out of it. So this is a vulnerability and risk assessment that we did, and it's a bit more on the qualitative side, but it all is rooted in the climate data and information. And you can see there's hundreds of stickies on this board that I had to sift through very detailedly, unfortunately, but I still get nightmares. But this is what you get at the end of the day after you look at that increase in the number of plus 30 days or in a decrease in precipitation. You get all of these consequences that are very, very specific to the context in which individuals are working in. Next slide. Which I think is maybe just Matt. And one of the other things is like we talk about this sort of qualitative higher level information. We bring that through with the videos that we make as well, and we've already seen, but we have quite a number on the atlas that are focused on wildfires and forests and what the impact is around climate and how communities are dealing with it, and bringing in that element of hope and seeing what is those really good practices that are coming in on the ground and people who are considering this in their work. And one of the things that's worth mentioning too is it's sort of a partnership in working with communities and individuals who are working on the landscape, but there's also really lovely partnerships that are going on with the people who are working in the space too. Right now, we're sitting in the PCIC and PICS offices, and when I should be in minus 30 in Winnipeg. So that's nice, I'm in Victoria, but I think it's this great space where we're working with PICS to like continually update the data and make it the best available information for individuals to use in their planning. And so that's kind of where these collaborations between partners, but also between these organizations is really a great space to be in when we're dealing with this in Canada. So I think that is something just maybe worth flagging at the moment. And I think Matt is going to go on next to do a nice demo of the atlas for you. So you can actually see how to get to the data, how to dig into it, how to download it. Yeah, and all those fun details that are far too detail oriented for me.
Okay, sounds good. Thanks, Christy. Yeah, so this is the ClimateAtlas of Canada, and this is one of the online tools that we've developed, and it's really designed to make climate change more approachable and relatable for people living in Canada. It does this by combining climate science, mapping, climate data, and storytelling all in one place. And Ian's just scrolling through the homepage right now, and this is some of our featured content that we have on the site. And you notice there's a lot of Indigenous content being promoted on the front page, and we'll get back to that in a bit. But there's a plethora of resources, from plain language articles, special topics around key areas and how they relate to climate change. And then there's also a whole archive of short documentaries that tell stories about climate change from the local perspectives, where people from across Canada talk about the impacts of climate change and how they're dealing with the challenges it presents, but also with a message of hope and a framing of hope, because that's really important. So if you have time, there's lots to explore. About the map and the climate data that we have available. And so this is the map page, and it is showing how climate models are projecting the future climate to be in Canada based on different greenhouse gas emission scenarios. So the Atlas uses data from 24 climate models and 2 different emission scenarios. And that data has been downscaled to more accurately fit the local topographies in Canada. And the data itself comes from Fyke, where we are right now. It's a research center located in Victoria, BC. So the data set consists of modeled daily temperature and precipitation data for almost 150 years, so from 1950 to 2095. And it covers all of Canada. So this data set is trillions and trillions of numbers. And so what we've done is we've taken that data set and we've processed it and summarized it in order to present it in a more digestible format, so as interactive maps and graphs that you can use. So the end result is we have over 2,000 maps that are available that show the average of the 24 climate models for a given 30-year time period and for a given climate variable, all of which can be adjusted. So the way to navigate the Atlas is through the buttons on the bottom of the page. So there are buttons and sliders that you can control. We've categorized the climate data into different variables that we thought would be more useful than just simple temperature and precipitation data. So we have hot weather variables, cold weather variables, general temperature if you still want to look at mean, maximum, and minimum temperatures. We have precipitation data, precipitation variables, as well as that also break out into monthly, annual, and seasonal, but also look at things such as number of wet days or number of dry days. And then also we have agricultural related variables. So things like the frost-free season, or the date of the first fall frost or last spring frost. We also have organized these into different time periods. So you have the option of choosing between 3 different time periods. We have the recent past, which is 1976 to 2005, which is kind of like the baseline period before we start implementing the emission scenarios. Then you can choose between the immediate future, which is 2021 to 2050. And then finally, you have the near future, which is 2051 to 2080. If you're looking at a future time period, you can also choose between 2 different emission scenarios. So we have, you can choose between less climate change, which is the low carbon emission scenario, which is RCP 4.5, or you can look at more climate change, which is a higher carbon emission scenario, also known as RCP 8.5. So all of these different options change what sort of map you're looking at. And so there's a lot of different varieties and combinations you can look at. There aren't any specific wildfire variables, I would say. However, there are variables that still might be useful, such as variables that look at extreme heat or dryness or wetness in particular areas. So the map does a good job of showing spatially what the climate models are saying. but you'll notice that each part of the map can also be clicked, every place name, every grid square. And when you click on it, a sidebar pops up that gives more specific information particular to that region. And so you'll get the whole 150-year time series that shows all of the model output for that period, as well as more specific information such as the model range, and then options to look at more detailed information, but also download images and CSVs as you see fit. So this is our the local data page, or a way to show to explore the data in more detailed fashion. It doesn't seem to be loading right now, but this is where you can download the data files as well as view the data in different forms, such as 4 different types of graphs. Yeah, navigating around the atlas is as simple as Google Maps. So clicking and dragging, you can zoom in and out. And as you zoom in, more locations become available for you to explore. At any given time, the title at the top shows what we're looking at. So right now we're looking at the average number of very hot days, or days that reach 30 degrees Celsius or higher, for the high carbon emission scenario, or what we call more climate change, for the 30-year time period, 2051 to 2080. On the top left is the legend, which shows what the colors represent on the map, or the values they represent. And then there are more options on the right hand, or on the left hand side, and these buttons adjust different aspects of the map, like how large or small the grid squares are that you want to view, if you want to look at the map from an average perspective, or if you want to look at how things have changed from the recent past, or delta maps. And then you can also select what sort of place names you're seeing on the map. So we've recently added a whole data set that looks at First Nations, provides First Nation community level data for over 500 communities across Canada, as well as Inuit communities. I believe there are closer to 20. And then finally, we have a selection of Métis projects that look at different aspects of climate and going on in the Métis Nation. I think this might be a good chance to throw things back to Ian if you'd like to talk about some of the new Indigenous content that we've added, integrated into the Atlas over the past year.
Yeah, and that was a major effort. So the Assembly of First Nations, the Métis National Council, and Inuit community or Métis communities and Inuit communities were quite involved in the development of this tool. And it's the first time that all of these data have come together for these communities in this kind of portal. And so to kind of just finish up the presentation, we were quite excited about that. The partners were quite excited about it. But as Christey was saying, you know, the data alone is not enough. And so how do we make this useful and relevant to communities? And we're talking about decision making as the title for the talk. To kind of set this in motion, we actually had a gathering in Manitoba at the Turtle Lodge with Inuit First Nations and Métis leadership. On the left there, Loxley, the acclaimed kind of Inuit climate advocate, was there giving guidance on how you build a tool, how you bring these different diverse data together. The tool was finally launched in March of 2022, and it is again a really important opportunity to look at data in different ways with different communities foregrounded, and Indigenous knowledge is also connected to climate data, and we find that to be quite important. But where do you go from there? We applied to Infrastructure Canada for a project, and we're in the process of developing a decision support tool for First Nation communities in particular. And so we're actually trying to figure out how to, you know, make sure that we have community input, Indigenous wisdom, First Nation knowledge is connected to climate data for applied decision making. And so that process of developing that project is underway, and linking that adaptation planning process, climate data, and Indigenous wisdom to make sure that decision making is well informed from multiple perspectives. And so that's kind of where the project is and where it's going. And we just want to thank you for the opportunity to present here. And Christey and Matt, if you have any kind of final comments, we're kind of wrapping things up. So thanks, everyone.
Thanks for your time, everyone, and thanks for listening to us. If you have any further questions, feel free to reach out. I'm happy to chat. So.
And that concludes our presentation. Thank you.
Thank you, everyone.
Well, excellent. Thank you very much. I don't see any burning questions in the chat, so maybe we will move on to the next phase of the operation. We'll turn over the baton to our next presenters, who I forget who is going next, actually.
So next up is ClimateNA.
Didn't realize I'm the second. Sure. Hello, everyone. Thank you for inviting me to participate in this great event. So here I will share my screen. Okay. Here, screen. Can everybody see my screen?
Looks good.
Good. Okay. Yes. The image on the title page already tell the major information of my talk. Okay. The topic is scale-free climate data for historical and the future periods. So the fundamental of my talks already is reflecting by this publication co-author with Dr. Hamann and also Dr. Spidelhaus and Dr. Carlos. And this is the latest paper describing the fundamentals, but we also had an earlier paper. People are citing both papers. So here is my the outline of my talk. First of all, scale-free climate data generated by dynamic local downscaling, then followed by the downscaling GCMs and the historical data and some additional features. And at the end, and I'll show how to access to those data. Okay, so the most climate data nowadays delivered are in the graded format or in raster format. For example, the most widely used climate data, WorldClim, the lowest resolution is 800 meters for some period, but most are still in 4 kilometers. The PRISM widely used in North America is 804 kilometers. The global coverage from the CRU is 50 kilometers. The GCMs, 80 to 400 kilometers. Even the highest resolution, for example, from the PRISM, and in the mountain area, the temperature change can be by several degrees within a tile. So that can often lead to the problem in developing ecological models use this kind of climate data because it does not reflect the exact climate conditions at a specific point, specific sampling locations. To overcome this problem, we need to develop a dynamic local elevation adjustment system. And the major challenge for developing this one is the lapse rate varies over locations. There's no constant value to make this adjustment. So we need to find a lapse rate for each specific locations. So we use the local variation in climate among the neighbor tiles and with elevation to estimate lapse rate. What we did is that if this is the interest of the point of interest, the program extract the 9 cells around it and then calculate difference in climate variables here and also difference in elevations. Then we develop the regression, simple regression then we use the slope of the regression as a lapse rate to make adjustment. This is for this point. If the point move to a different location, we will extract a different group of tiles to make a new lapse rate. That's why we call this a moving window or dynamic local downscaling. By this, we can convert the graded climate data into scale-free climate data. So we can get climate data for each specific locations. And this is the map, show the beauty, but it also shows the effectiveness in statistics. For example, we have the weather stations. We use BC as an example. And we have weather station observations. We have data from the original prism in the red points and also the downscaled one. You can see the difference. The black points is downscaled one. The R square, the relationship with the weather station observations improve a lot. You can see the difference. And for different variables, for different months. And we also derive many additional climate variables at the annual level, seasonal level, and the monthly level, totally over 200 climate variables to reflect temperature, precipitation, dryness, and many growing degree days, which are often used in developing ecological models. So the difference is if we use the original prism data in the graded format, and this is the effect accuracy we can achieve in modeling the ecosystem classification in BC. You see the accuracy is not great. But if we apply our downscale scale-free climate data, we can sharpen it into a much better simulation results. The similar things occurred in other example. Some people use the graded climate data to develop a species distribution model for Douglas fir. You know, Douglas fir has been introduced to Europe, to many countries, very successful. So they want to build a model with North America data, the native distribution data, and to predict if the model works for Europe, if the model can find the suitable climate conditions in Europe. Their conclusion is fails, is only less than 10% can be identified. But at the same time, I also did the same thing. When I see their results, I was shocked because I did the same thing and it was very successful. The accuracy rate can be nearly 90%. So I was wondering what happened. So I followed their approach to use the, instead of use scale-free data, I use also the 4 kilometers grid data and follow their approach. Then the model accuracy decreased to 20%, but better than theirs, but there may other factors involved. Anyway, we can see the effectiveness of the scale-free climate data. The second part is how to deal with the future data and the historical annual data. You know, the future data is even at a much coarse resolution. It's from 80 kilometers to 400 kilometers. And for example, in BC, we only have 9 points here. And this data, if we just interested to look at the global trend, this is okay. But to develop a local adaptive strategies, this is useless. So we need to do the downscaling. The approach we applied is to take advantage of our scale-free data. So what we did is that for the future climate data from GCMs, we consider as a whole, absolute value as a whole. Then we split it into 2 parts, the changing part and the reference part. And because we have the reference part predicted by scale-free climate data, ClimateNA or ClimateBC. And for the change part, we don't have data, but we can interpolate it into a continuous surface. Then we add them together, and here is the interpolated change, and put the interpolate on the baseline data. We will get future climate data in high resolution. So this method later on was also applied by World Climate, but the difference is our scale-free data has advantages to make this replacement. And the World Climate data or other climate data, they only can use their graded data as a reference to do the replacement. So this process achieved 2 things. One is downscaling, another is error correction, because we correct the reference major part of the climate variable. For example, we look at one weather station in Vancouver Airport, International Airport, and from the GCM, it tells average of 20 GCMs, the temperature currently is 4 degrees here, but observation is 10 degree, nearly 10 degree, and our prediction also 10 degree. If we look at the future, we can correct this error by this much, by 6 degrees. And if we look at the future, and their future predictions for 2020s is still 5 degrees, but our prediction is 11 degrees. You can see this is very unreal for specific points, but the ClimateNA can correct that for most part of it. And also, for the historical years, we have both observations, we have model predictions. And for the GCM for this year, across North America stations, and their relationship is 0.58. That means the future, the prediction from GCM can only explain about 60% of variation, but ours can explain over 70%. But people realize that the GCM has a problem. Then many people use the RCMs, regional downscale, the future climate data. The RCM is better than the GCM, 0.6, but still our is better. And for the new GCM, so earlier we used RCP, now we switched to the new version, the social shared pathways, SSPs now. And we had a paper by Colin, me, Andreas, and Alex. So we describe how to make selection of the GCMs suitable for different areas, and we integrate into ClimateNA. And next part is newly developed historical data. We used climate data from research climate research units in UK. And here, this part shows the variance explained. If we directly use the 50-kilometer data from CRU, and the variance explained about 70%. But after the ClimateNA scale data-based correction, that can reach over 90%. But still, I got a lot of complaints that the CRO data is getting worse. And when I check their number of stations used, the number of stations used for North America is few hundred. It's a very small number. So we developed it from several 10,000 weather stations from the global historical climate data network. And from the daily data, we developed the monthly data. And that one improved a lot, but at least to some extent. I got good feedbacks on the new changes. And next is to introduce some additional features of ClimateNA. And the first thing is this all-in-one package. We have the paleo, historical, and the future period all in one package, same unit, same resolution. And for the paleo period, we don't have that yet from the new GCMs. So this part need to use the old version. And we have historical and the future ones. And another function, useful feature is the time series function. And for historical years, the climate allow you to get historical time series for multiple locations for multiple years in one run. So you can directly compare the trend also for the future periods. Another new feature added is the map in, map out feature. Earlier, we only allowed to use the spreadsheet as an input file. Now the ClimateNA can directly read the DM raster file and generate climate maps. And the spatial climate data was hosted by AdaptWest, and also Andreas also have a website hosts a lot of data. But to serve as a complementary feature to those data portals, I developed a new portal to allow users to download individual climate variables for a specific period. And for North America, whole North America, or for West North America. And we have a map version, allow you to click here on it, and then the climate data will show up. It's for the historical period or for the future period. And also allow you to save to your own computer. For the occasional user, this is very convenient because the longitude will be automatically obtained by clicking on the map. Then you get the data right away for the climate data for the specific point. And last year, I also developed a web API version, which support web application like the one I just showed, and also the mobile applications. And yeah, you can integrate ClimateNA into different kind of applications. And under the request of some users, I developed a new function called the command line function. This allows the ClimateNA to be called by other programs. That can be considered as a desktop API because the web API has a capacity limitations. Currently, I only allow each user each time to get climate data for 200 locations. For the desktop API, you can get climate data for unlimited number, millions of locations, no problem. And to use those features better, I developed R package. So this includes some functions to obtain the spatial climate data downloading by specific group of climate variables, specific period, make it very easy. And also to stack those variables together for spatial predictions, and also for a wrapper, our package wrapper, to call the web-based, the desktop-based API, and also the web API can also be called in R. So this allow the ClimateNA totally integrate into our programming workflow. At the end, how to access to it, and go to the ClimateNA.ca page. You click on the image, it will lead to this page. In this page, you can register, and then after you register, you will be allowed to access to download page. And then you fill in some simple information, then you can see the download page and show the information, the package there, and all the package are accessible there. And that's it. I would like to acknowledge the funding agencies and the people and the AdaptWest to host the spatial data. And thanks. And any questions?
Thank you very much. That's looks like an amazing set of tools there. So thank you for sharing about them. One question that did come up is basically, and I think it was in the context of the downscale. How do you account for the heat island?
Heat island. Oh, you know, the downscaling is based on the we use the PRISM as a baseline data, and for the area PRISM doesn't cover, we use the world climb as a complementary to make the full coverage. So the downscaling totally based on the grid data, and the mountains, the big aspect are considered by the baseline data. For the local downscaling, only elevation is considered. Andreas, you may want more.
I can add to this. So basically all kinds of, well, the way to think about it best is that ultimately, sorry, should I continue?
Yeah, please.
Ultimately, everything that is in that package is based on standard weather station data. So the only thing you get is basically open field conditions with a standard weather station adjusted for topography. So everything else, small heat island effects that are not necessarily captured by weather stations, although they may. If you have a big city like Edmonton in a cold area, you may actually model that heat island effect partially. But normally, I would say any kind of micro climatic effects are not in there. So effects of, let's say, shading or you know, in a small valley or something like that. Those things, anything that's not topography, that's maybe due to vegetation or other lake effects, or as you said, heat island, those would not be on there. Yeah.
Yes, if those effects not captured by the baseline data, we don't add, we cannot add into it. We just improve the baseline data.
Excellent. Thank you very much. And one more question has shown up here, which I will relay. Does the website allow the choice of which I can't speak, IPCC RCP scenario can be used for the model prediction? Is that selectable?
Okay, the web version only show the latest SSP. If you want to still use the RCP, you can download the package, the version 6, still include the RCP there.
Excellent. Thank you very much. I think that brings us to the end of the questions on this. Thank you for your presentation and responses to the questions. So we'll turn it over, I guess, to Jeremy. Yeah, please.
Awesome, thanks. I'm assuming you can see and hear me and the presentation. Maybe just let me know if that's not the case. So thanks for having me, everybody. And what I'd like to take a bit of time to share with you all after those great talks is some work we're doing at the Canadian Centre for Climate Services in real close coordination with folks at the CFS and a whole host of people who've been helping advise us on this and others, is work to develop climate change projections of fire weather index system indices. So these are measures of weather and climate that, as many of you probably know very well, are specifically tuned to speak as eloquently as possible to those measures that are really relevant for wildfire, you know, hot, dry, and windy. And so what I'll do now is just give you a quick pitch of where we're at with this ongoing project, where it's headed, and ideally when this will be released to the wild for everyone to use. Okay, here's the wildfire trilogy. Again, preaching to the choir here on this slide, I'm sure, but wildfires are a combination of, wildfire risk comes from a combination of weather and things that actually can light the fire, so lightning or humans, for example, and then the availability of actual fuel to burn. So if you have, elevated conditions with respect to all of these, then you have potentially high wildfire risk. Where we're contributing in our project is specifically to the weather aspect of the fire trilogy, so to speak, at the Canadian Centre for Climate Services, and our partners. We can geek out on weather and climate, but we're not so well placed to speak to ignitions and vegetation, especially how these things will evolve over coming decades. And so what we're providing here to the conversation is information on how weather that's pertinent to wildfire will change now and into the future. This project has been going on for I'd say over a year now, or in earnest, and well over a year now, actually, come to think of it. And the first part of the project for us was to really sanity check with potential users of this information what kind of decisions they would be basing, long-term future projections of wildfire weather on. And so this is a beautiful decision map from this paper referenced in the bottom right. And we found ourselves, this was referred to us by one of the many folks we got these sanity checks from early in the project. And we came back to this quite a bit in terms of thinking about the information we were providing and where it would provide the most use. And so it's a beautiful image that shows on one axis the spatial scale of decisions, where are they occurring on a meter scale or across the whole country, and then also the timeline. So decisions in the wildfire context can be on the order of seconds, who to evacuate, where to send the helicopters, this type of thing, all the way up to multiple years. Decisions like how to fund fire facilities, how much staff to bring on board, big major asset purchases, things like that. And so we're talking in our project about long-term projections of wildfire weather conditions. So those really, in our mind, are informing the decisions made out at the right-hand side of this plot. So we're thinking about informing those strategic decisions, which guide, in many cases, how able agencies and municipalities and insurance and et cetera, are able to make those shorter-term decisions. So given all that, our objective, in as much of a nutshell as we could put it, was to provide national scale, national coverage, fire weather system component, future projections to support really strategic fire preparedness and response planning. So that was our guiding principle that we used as we dove into data and downscaling, et cetera, et cetera. Now, I won't get too much into the details of the data itself. We have in development now some very deep technical documentation that I'm happy to share when it comes out. Suffice to say, what we are aiming to do is provide future projections of the indices of the fire weather index system. And so these are things like FWI, DC, Fine Field Moisture Code. Sorry for the acronyms here, but I think a lot of you probably know what these are. These are the core projections that we're making, and we're making these across the country in a gridded sense, but we're also diving down and trying to make projections of these variables, these indices, at local scale. So actually bias correcting down to the location of stations where these are calculated based on observations. And so here's some snapshots of output that we're thinking about developing and serving publicly. So we can talk about changes to things like extreme annual fire weather index, FWI, how that changes from essentially today out to the end near to the end of the 21st century for different climate scenarios. We are exploring ways to share this information that reflects that year on year FWI, and especially that extreme measure of FWI. That's really important for wildfires. That varies, of course, right? The climate goes up and down, there's El Niños and stuff. So we can talk about shifts in those extreme dangerous FWI conditions through plots like what you see on the right hand. So shifting distributions of those extreme summer conditions. Now, I'm talking about FWI, and I think many people in the room here, I recognize the names from having spoken with you in the past for this project. So thanks. I'm going to say thanks to all of you who are here and we've spoken to. This really helped guide us. A lot of people here know FWI, and it's a bit of a practitioner language, so to speak, but we would also like to be able to reflect what we think is really valuable information in a way that the general public or municipal planners or the insurance industry can understand. So we're slicing and dicing this information also in ways that's a little bit more digestible. So here's an example of changes to the occurrence in terms of days per year, in which on average, a climatological sense, fire hazard is at a particular level. And we can pull out really interesting information and sometimes kind of scary information out of this kind of plot. So this is showing, for example, the number of days where this particular arbitrary location, Springbank, Alberta, is sitting in extreme fire weather conditions is going to kind of like double. It's like the size of that red rectangle at the top there. And so we're developing ways to communicate out this sometimes kind of technical information in ways that's digestible, right, to people besides those practitioners like yourselves who are really often fluent in the technical aspects of fire weather and fire risk. This project is ongoing. We're starting to wrap up our data generation process, which involves downscaling and use of multiple climate indices. Temperature, precip, wind, and relative humidity are the key ones here. And so we've done a lot of fairly technical downscaling, and we're making sure that data is right. At the same time, we're developing ways to share that data online. And so what we're planning on is to provide this information in terms of like an online app would be very much likely associated with climatedata.ca, but it might look a little different in the sense that we really want to provide users as much flexibility to explore the data as possible, both in terms of which component they're interested in of the FWI system, but also with respect to, what level of extremes matter. We learned through talking to many of you that fire weather and fire danger are looked at differently in different parts of the country, up north, east, west. And so it is valuable, we think, for us to provide this information in a way that's as sliceable and diceable as possible by the user. So we're not providing one or two standard indices that may not apply to, your particular location, decision-making context, this type of thing. So this work is underway to develop a delivery mechanism that gives you plots, gives you the data itself, and also, of course, lots of context and learning for those of those visitors who aren't fluent in this stuff already. That's about it for this really quick elevator pitch of this ongoing project. I always am scared to give timelines on this type of stuff, but I will say that our goal here is to get this project wrapped up and delivered, with things like bilingual translation and learning zone material and a lot of other stuff by the end of this calendar year, if not sooner. So I'll say that now, and you can hold me to it as December approaches. But that's our tentative timeline to get this out in the wild for people to use in real world decision making. If you'd like to learn more about this, just drop a line in chat, email me. We're looking potentially for people to play with our prototype app and that kind of thing. So if you're interested in that, reach out and we can chat. I'm also happy to answer any questions now or later. Thanks.
Perfect. Thank you very much, Jeremy. We have a couple questions. One is having to do with the future FWI system. Do your calculations allow for changes in the fire season length, either explicitly or implicitly, I guess?
They do, yes. Yeah, in the sense, if I understand the question right, we're taking things like overwintering into account, and those are turn on and off at sort of inside the model, so it recognizes that type of thing. In fact, fire season length is one of the outputs that we would like to share that come out of this, so we can look at fire season length, probably for the most part increasing in many places in Canada. That would be one data product and information product that we can share. Hopefully that answers the question.
Yeah, I think so. And if not, I'm sure there'll be a follow-up.
Yeah, okay, cool.
So the other comments that are there have to do with does your system or does your approach consider lightning or ignition cause at all into the way you're calculating it? As there's sort of expectations that lightning will increase with time. So
yeah, of course, what we're providing is information that's based entirely on meteorology. So to be specific, we are bringing in historical and future projections of temperature, precip, relative humidity, and wind, all on the daily scale. And so that's the information that is used to develop FWI in general. What's not there is things like changes in lightning. That's one of the other parts of that fire trilogy, or the fire triangle, right? And so you would combine, in theory, our information with information on increase in lightning strikes, and also in the ideal world, changes in fuel load and things like that to get the full picture. So what we're providing is kind of an important part, but not the entire thing.
Excellent. Thanks very much. And there are comments there's also a comment that others are working on incorporating sort of future lightning predictions.
Oh yeah, Cindy, we should, that looks really cool. Okay.
And I know Mike Flanagan is still online. I don't know if you want to weigh in on this topic because it's one of his passion areas. So.
Hey, Jeremy, thanks. Yeah, lightning is really important to the fire community because, area burn in Canada has doubled since the 70s, but human-caused fires have been going down in numbers and area burned, whereas lightning-caused fires are causing all the problems. So looking into the future, if we can understand how much lightning we'll see, along with how dry the fuels are, it can help us look at future fire regimes. And currently we have models in fire occurrence prediction for lightning and human cause. So having this kind of work done, and Cindy, your comment is great. I look forward to seeing that. Currently we use a European model for lightning forecasts, but lots of work to do here. And so great to hear. Thanks.
Excellent. Thank you. There's one more question here about data services, and it says, will you be providing an ArcGIS, it says REST service for the data?
Yeah, great question. Well, the plan off the bat would be to provide the data in a few kind of standard formats that are familiar to the climate world, at least. So we would definitely, I'm sure we would be able to consider a ArcGIS REST API. one of the factors in this data and climate data in general is there's often a really important time component. So it would, part of the thinking there would be how to reflect, what is essentially time series data in a ArcGIS REST service. So that, I'm sure it's tackleable, and we could talk about that too. I think it's a question that goes beyond just climate data for fires. It's ArcGIS is an important platform for many users. So.
Excellent, thanks very much. And there's a comment here as well, and it's an interesting question, probably a little bit out of maybe beyond the scope of what we plan to talk about here, but is the fact that we're seeing increase in lightning reflect the better detection that we have. We've really had lightning detection in Canada since the early 80s. And so as that network is growing, are we actually detecting more, or is there actually more in that trend and in that trajectory of data? So I think it's an interesting question, maybe worthy of a whole seminar all on its own. So. Okay, I think, unless I missed something here, we have sort of had a chance to respond to or present all the questions that I've seen. I will do a last call for questions. You can either type one in, or if you want to unmute, that's also an option. Like an auction, going once, going twice. Okay, well, I guess I want to repeat my thanks to all our presenters. I think there's been an enormously interesting and quite a lot of data presented and information that we've had, which will keep some of us clicking away on our computers for hours in the future. And so I really do want to thank you for taking the time, to those who presented, and also the time to those of you who were able to join us. I hope you found this interesting, and we really appreciate you have.
Sorry, Brian, I muted you. We actually have one more presenter. We still have Dr. Hamann, who's going to be talking to us. It's been a morning over here, everyone. So we have one more presenter. Andreas is going to be talking to us about some general basic stuff to do with how to deal with climate data, kind of best practices, I guess. So with that, I'm going to hand it over to Andreas. Thank you.
Okay. How's this? Can you see this? Shared screen?
That's perfect. Yeah, it's perfect.
Okay, good, very good. Well. So I think the mission for me was, Andreas, we have more than an hour left at the end. Can you fill this somehow? But maybe I should just keep it short. So we have already had quite a large range of really good presentations, and we use that most of the time. So I think I can keep this relatively short. What I want to add is some additional resources that were derived from ClimateNA and that are available. So Tongli and I figured that we break this up. So I'll talk a little bit about the gridded data resources that are available. I should say I'm not 100% sure if I fit perfectly in, but we've had a broad range of talks already, from having an indigenous component to and also very different target audiences for the products that were available here. So many things are just visualizations. Others were really deep dive technical towards a technical audience. I'm kind of sitting in between. I think when Tongli and I started this 15 years ago, our primary target audience for this data product were Tongli and me. So we were doing this for ourselves. We needed some tools to support research. And so my perspective or my audience is generally people who do original research, who want to have access to the data in numerical format. But maybe not to a degree where you do all your interpolations yourself, things like this. So one limitation that's probably important from fire perspective, is that our data source, our databases are not daily data. So our temporal resolution is monthly data, that's it. And daily data is important for many applications. So we are using, even I working with trees that have a fairly long time span, sometimes we do need daily data and we're getting it elsewhere. So yeah, there are obviously other sources that provide this. But monthly data is good in many cases. And there's also a way to kind of squeeze daily data into monthly reports by using bioclimatic variables. For example, I can estimate growing degree days, number of growing degree days. Usually you would have to do this with daily data, but as it turns out, you can estimate this very accurately from monthly climate data as well, or you can calculate probabilities of an expected extreme event given for a given month based on a mean annual, based on a mean monthly temperature. So especially for the future, that often works. So rather than working with actual daily data, we just do monthly estimates of what a daily extreme would be in that month, things like that. So the data set does have 33 bioclimatic variables, some of which I just mentioned, something like growing degree days or chilling degree days. There are also 48 monthly standard variables. And so you can use either the ClimateNA software to query it for a particular location or query custom grids. But one of our collaborators, Carol, has actually generated those grids also for different climate normal periods. So 61 to 90 here, 91 to 2000 being the latest, and then the same for all the future projections. And you can get those as zip files. I'll just show you how they look like. So at 1K, this is a fairly fine resolution grid of mean annual temperature. And there are many other interesting variables in there. So I'm just giving you here a few examples that are kind of interesting. So we use PRISM data that's behind this from Oregon State University, Christey. It does do some things that other data products don't do. For example, here at the south of BC, you see those interior valleys have warmer temperatures than the mountains. But in the north, in winter, this is reversed. So you get basically the coldest, you get these temperature inversions with the coldest temperatures in the valleys. And this has real ecological consequences. For example, up there, I've actually visited there. I did a hiking trip there. You have a reverse tree line. So the bottom is treeless. And then as you go up the slope, the trees start growing again. So these kind of temperature inversions and climatic anomalies that are very well modeled by PRISM. They are real, and the same, for example, for MSP. That was growing season precipitation. You have these really hard rain shadows here along the mountains or Saanich Peninsula here, or any of the Rocky Mountain areas. And those are also real. So if you drive through over a mountain pass, it's like you open the door into another world. All of a sudden, you are into a completely different set. So this is really nice baseline climate data, and we like it for that reason. I don't think there is much out there that's similar. I think the Chelsea precipitation data set gets this a little bit, but not nearly as well as the PRISM. All right, and then, as I said, we have a bunch of derived variables such as precipitation as snow, climate moisture deficit. So these are all variables that can be estimated with very high reliability, even though they often would require daily data. Now, Carlos' website, so on Climate Basin, I can never find it, but if you Google ClimateNA and Climate Basin, or data basin, sorry, you'll end up at this page. And so I showed you the header, but it's really a huge web page. So you get all the different different scenarios that are out there. So for each of those future projections, you get a zip file with 33 of those bioclimate variables at this huge resolution. So it's this enormous amount of data, and you're often kind of at a loss how to deal with all that data and how to start with it. So I wanted to give you a few pointers as to how to make use of this database, or also ClimateNA. So first of all, I should say that this is also already a very curated selection of future climate models that make the cut. So Colin went very carefully through it. I think he had 9 criteria on how to evaluate the quality of future projections. So we basically, of the CMIP6 multi-model data set, a lot of them were excluded for various reasons. And the ones that are left, they are a good representation of what future climate will be. So they try to capture various multivariate clusters and future projections. And they also have high quality characteristics. So that's the first step to boil it down a little bit. So whatever is on Carlos's website is already a cut back version of the CMIP6, but it's a curated one that I think is pretty good. And then you still get 13 models to select from. And I just want to give you a few strategies of how to go about it. So one is to just work with an average ensemble. So you take those 13, or maybe a smaller set of 8 that excludes some extremes, and average them, and then you have one climate model that you can deal with. So that's one thing. And our download statistics tell us that this is what almost everybody does. Now, that's not super, because especially in terms of precipitation, one model says it's getting a lot wetter, the other says it's getting a lot drier, and then in the end, many areas, the averages or everything stays the same. But that's not a good assumption. So you do ideally want to look at more than just the average. So what the next thing you can do is select from clusters that are similar. So we included this kind of cluster analysis for how similar different climate models are, their outputs for seasonal precipitation and temperature. So you can select one from this cluster, one from the next, one from the median, and one from the top cluster. So that gives you a good representation without necessarily running all 13 models. Another option, if you select, or if you work very locally, you might want to look at regional selections. So not everything that's not every median scenario for North America is median where you are. So basically up here you see all the states and provinces of North America, and then you see how they what the predictions of individual models are for specific locations. And you can see in terms of precipitation, that can be very variable. So depending on who you are, your median scenario is not the same. And the fourth one that's also included in that paper by Colin is a sort of a multivariate pre-selection that considers multiple variables and where they sit. So basically the way this works is if you only can do one scenario, then you can use the ensemble, or if you want to pick an individual scenario for any of those regions here, for example, Western North America, we go here, it says we should pick MRI. So that would be in multivariate space, that would be kind of the closest to a mean scenario you can run. Now, if you say, okay, I can run 3. So I want a median scenario, a somewhat optimistic, somewhat pessimistic scenario. So that, well, in multivariate space, it doesn't select the extremes, but something between the extremes and the median. So if you wanted those scenarios for this particular region, it would be MRI, UK, and MPI, and so on. So, and depending on how many you want to run, you just add additional scenarios from this table for the region that you're working with. So that gives you a good representation of different scenarios. Now, the last thing I can recommend is run everything. Run all the variables for all the models and for all the time steps. And so this is what one of my PhD students had done recently. So basically, this is a study of, so the white area here is spruce habitat. It's just an example application, but you can do it for anything that would apply to you. So we can look at this area and where it's projected to be for all variables. So in this case, it's a multivariate visualization, so a principal component analysis. So these stand simply for many variables that represent in total something like 90% of the climatic variance in the province. And you can see where all those individual climate trajectories go and at different time steps, just to get a sense of how variable things may get. So on average, so along this red arrow, that's kind of a vector through that climate space, or through the climate space through which we are projected to go into the future. You can see that the direction is pretty reliable, but there is, as we go further into the future, there is quite a bit of variance that we have to anticipate, so where things could go. Now, it seems daunting to run all these things, but it's actually not that. Also, sorry, before I continue. So the reason why you want to do this is that in the end, you can actually simplify your problem into a univariate, simple climate vector over which you want to make your predictions or predict your response. So we have all the climate variables summarized along this vector where we are headed. So this becomes my new x-axis, and then whatever you do, fire frequency, height growth of spruce trees, and so on, you can model this very simply across this one dimension. So I think that's a very nice and elegant way to take full advantage of that whole climate database. Now, as I said before, it seems a little bit daunting because it's so many variables and so many future scenarios, but it's really not from a computational perspective. And one of the reasons is, as Tongli already pointed out, that the climate projections are actually at very low resolution. So these are the effective topographic resolutions of the different climate projections of the different climate models, and that even overstates it. So if I look at the actual projections, they are often very homogeneous. So even though I have that topographic resolution technically, these are so the second row down here, those are the same change projections, the observed and the predicted. And really, we can get away with a single point, with a single grid cell for Alberta, for example. It's a fairly homogeneous environment. They may be a little bit different in the mountains, but generally, you don't have to really work at very high resolution if you want to explore the overall variance across all the different climate models. So you can work with all variables. You can work with all future projections for different time periods, from different models, for different scenarios. It doesn't matter if you work at relatively low resolution. It's not a very big. You can do this in Excel essentially. And the last thing I would also recommend is, in addition to the climate projection, use the real thing. So use the actually observed climate change. We have it now fairly prominent. So this is a anomaly map from a little while ago. So we haven't updated it to 2020 yet, although it is updated in the software. So you can get these surfaces for the 1990 to 2020 period. So if we look at the difference between those two layers, 61 to 90 average, and then the next climate normal period, that's the climate change that we have actually observed. And it does resemble what's being projected quite closely. So you can, that's to me, that's actually the most important thing, that we adapt to the climate change that has already happened. So going from the square here, which represents the historical climate average, for which much of forest ecological management has been designed, going to the 2000s. So we can only assess the 2000s at the moment, even though you may feel like you're in the 2020, we do have to work with 30-year normals, right? So because climate is so variable, you do have to look at 30 years. So our next normal that we just got is 1991 to 2020. So that's a 2005 midpoint. So we call this generally 2020s. So we moved our climate space already quite a bit, not quite, but almost halfway to the next one, which would be the 2020s projections. So that would be my general recommendation, to, at low resolution, run all the different climate scenarios to see where you're headed, what the variance is, and then at high resolution that you can get from ClimateNA for any study area at whatever resolution you want, that's where you run your actual biological models. Okay, and I think that was my last slide. Yes. So I can take some questions if you want me to.
Excellent. Thank you very much. And I have to apologize for dropping you off my list.
Oh yeah,
down in the wrong order. So yeah.
You could have. I'm really unoffendable.
Thank you very much. I don't see any questions for you in the chat, but we certainly have a few minutes to talk. And if you anybody wants to unmute or type something into the chat, we certainly have some time. So. Okay, well, at risk of cutting somebody else off, I want to thank everybody again for participating, and thank you for these excellent presentations. There's a great deal of information to absorb and a lot of opportunities for us to pursue some directions. So thank you to each of our presenters, and thank you to each of you for coming. And we have our final February Flare-Up Friday coming up a week from today. So hopefully many of you will be able to return for that. Thanks again, and take care.